This is module 3 of chapter 1. In this module, we are going to discuss about Pfaffian differential equation. First, we shall define Pfaffian differential equation and then we shall establish the necessary and sufficient condition for solvability of a Pfaffian differential equation. And lastly, we shall discuss various methods to solve this type of equations. So, let us go to the first slide of module 3 of chapter 1. First of all, I am defining Pfaffian differential equation in this first slide. In equation 1, sum of fi dxi, it is called the Pfaffian differential, and the equation sum of fi dxi equals to 0 is called a Pfaffian differential equation. Here fi is function of n variables x1, x2 and xn. There is a fundamental difference between a Pfaffian differential equation with 2 variables and Pfaffian differential equation with more than 2 variables. So, we shall discuss the equation taking 2 variables separately, and later on we shall discuss a Pfaffian differential equation taking 3 variables. Therefore, a Pfaffian differential equation in 2 variables can be written in the form pxy dx plus qxy dy equals to 0, and this equation can be written in the form dy dx equals to fxy, where fxy equals to minus p by q. Now, the equation 3 is defined, that means the function f is defined if p and q are defined. Therefore, the equation dy dx equals to fxy can be defined. In particular, if p and q are single valued function, then f is also a single valued function. So, for that case, the equation 3 can be solved easily, and if we take the initial condition as y is equal to y0 at x equals to x0, then the solution of 3 is a curve which passes through the point x0, y0. So, the general solution of the equation 3 can be considered as a one parameter family of curves in xy plane, which is given by phi xy equals to c, where c is a constant. Now, I shall discuss how to find the integral of the Pfaffian differential equation with 2 variables. Let phi xy equals to c is an integral or solution of the equation 3. Then the p expression p dx plus q dy can be written as d of phi. Now, if we expand d of phi, we will get del phi del x dx plus del phi del y dy equals to 0. So, if we compare this equation with p dx plus q dy, we will get the relation 1 by p del phi del x equals to 1 by q del phi del y equals to mu, which is function of x and y, and this function mu is called an integrating factor of the differential equation. So, to make the equation integrable, we need to multiply p dx plus q dy with a factor mu xy, so that the expression mu p dx plus q dy equals to an exact differential d phi. And we can establish that for 2 variables, a Pfaffian differential equation always possesses an integrating factor. Now, we are going to discuss about a Pfaffian differential equation in 3 variables. Equation 5 is a general form of a Pfaffian differential equation in 3 variables. It can be written in vector form x dot dr equals to 0, where x is equal to PQR and dr is equals to dx dy dz. There is a lemma, a necessary and sufficient condition for the existence of a relation of the form f u v equals to 0 between two functions u x y and v x y not involving x or y explicitly is that del u v del x y equals to 0. This lemma can be proved very easily. If anyone is interested to see the proof of this lemma, they can go through the study material of this lecture. Now, there is another lemma. Let x be a vector function of x y z and mu is a function of x y z, then mu x dot curl of mu x equals to 0 if and only if x dot curl of x equals to 0, and this lemma is also can be proved very easily, and this proof is given also in study material. And these two lemmas are very important to prove the theorem which is stated here, and this theorem is very important in the sense that it says about the necessary and sufficient condition for the Pfaffian differential equation to be integrable. So, a Pfaffian differential equation x dot dr equals to 0 if this condition is satisfied, x dot curl of x equals to 0. Now, we are going to prove this theorem. We shall first prove the necessary part of this theorem. That means, we are first assuming that the Pfaffian differential equation x dot dr equals to 0 is integrable, and we have to prove that x dot curl of x equals to 0. Now, x dot dr equals to 0 means p dx plus q dy plus r dz equals to 0, and this is also integrable. Therefore, we can find a function phi x y z equals to constant such that del phi dx dx del phi del y dy plus del phi del z dz equals to 0. And if we compare this equation with the given equation, we will get a relation between p q r and the function phi, and this is the relation among them. Mu p equals to del phi del x, mu q equals to del phi del y, and mu r equals to del phi del z. So, mu x can be written as gradient of the function phi. Now, if we take curl of mu x, that gives 0. Therefore, mu x dot curl of mu x equals to 0. Now, if we recall lemma 2, it says that if mu x dot curl mu x equals to 0, it implies x dot curl of x equals to 0. So, using that lemma, we can conclude that x dot curl x equals to 0. Therefore, the necessary part of this theorem is proved. Now, we are going to the sufficient part of this theorem. That means, we are assuming that x dot curl x equals to 0, and we have to prove that x dot dr equals to 0 is integrable. So, to prove that, first we assume that z is a constant. Then the given differential equation reduces to the form p dx plus q dy equals to 0. And if we recall theorem 1, which says that a Pfaffian differential equation with two variables always possesses an integrating factor. Therefore, there exists an integrating factor mu such that this expression p dx plus q dx will become total differential of some function. So, let mu is our integrating factor. So, if we multiply this equation by mu, then we can write the equation in this form where mu p equals to del phi del x, mu q equals to del phi del y, and the equation becomes in this form. Now, this part del phi del x dx, now think z is not a constant. So, if we take z as a variable, then this part del phi del x dx plus del phi del y dy plus del phi del z dz can be written as d of phi, and the rest part is written in this form psi into dz equals to 0, where psi is the function mu r minus del phi del z. Now, mu into x, it becomes del phi del x, del phi del y, del phi del z plus psi. So, it can be written in this form grad of phi plus 0 0 psi. Now, if we compute this quantity mu x dot curl of mu x, that means del phi del x, del phi del y, del phi del z plus psi dot del psi del y minus del psi del x 0, it becomes Jacobian of phi and psi with respect to x and y. And we have assumed that x dot curl of x equals to 0. So, this implies, again applying lemma 2, we can write that mu x dot curl of mu x equals to 0. Therefore, this Jacobian del phi psi del xy equals to 0. Again, if we use lemma 1, that means if we use this lemma, it says that the function psi can be written as function of phi and z. Therefore, the equation 8 becomes d phi dz plus psi phi z equals to 0. So, you have to remember that this psi is now only function of phi and z. Again, this is a Pfaffian differential equation with two variables. So, it will also possess an integrating integral. Let that integral is psi, phi, capital Phi phi z equals to c. Now, replacing phi by its expression in terms of x y z, we get a solution in the form f x y z equals to c. That means, this is the integral or a solution of the given differential equation x dot dr equals to 0, or in other words, we can say that the Pfaffian differential equation x dot dr equals to 0 is integrable. Therefore, assuming the condition x dot curl of x equals to 0, we arrive to the conclusion that x dot dr equals to 0 is integrable. In this way, the sufficient part of this theorem is proved. Now, we want to apply this theorem to prove the solvability of a given Pfaffian differential equation. The equation is given in this form yz plus z square dx minus zx dy plus xy dz equals to 0. We have to prove that this equation is integrable. So, the capital X in vector form, capital X has the components yz plus z square minus zx and xy. So, curl of x for this example becomes 2x 2z minus 2z. So, if we compute this, x dot curl of x, it becomes after simplification 0. Hence, the condition x dot curl x equals to 0 is satisfied. So, using the necessary and sufficient condition of the previous theorem, we can say that the given differential equation is integrable. In last section, we have discussed about the solvability of a Pfaffian differential equation in 3 variables. That means, if a differential equation is given, we can check whether that equation is solvable or not using the necessary and sufficient condition of solvability. But how to find the integral of that differential equation is not discussed. So, right now we are going to discuss different methods for solving a Pfaffian differential equation in 3 variables. Now we are going to discuss different methods for solving a Pfaffian differential equation in 3 variables. Before discussing different methods, we are assuming the condition of integrability is satisfied for all the equations. The method 1 is by inspection. So, in this method we have to find the integral by inspection. So, let us take one example. So, in this example we need to solve the equation which is given here. So, first of all we check the integrability condition of this equation. So, capital X vector is y square plus yz, z square plus zx, y square minus xy. So, curl of x is this. So, x dot curl x becomes 0. Therefore, the given equation is integrable. Now, if we look at the equation, then it can be written in this form: total differential of some function d of z plus x by z plus x plus dy by y minus d of y plus z by y plus z equals to 0. So, after integrating, we get the integral of the given equation like this: y into z plus x equals to c into y plus z, where c is the arbitrary constant. Now, we shall discuss method 2, which is separation of variables. So, this is a special case when px, qx, qy and rz are functions of x, y and z respectively. So, if the equation is given in this form, it is easy to find the integral. After integrating the equation, we can get the integral in this form, where c is the integrating constant. Now, take us this example: yz dz plus 2 zx dy minus 3xy dz equals to 0. So, first of all we have to check whether this equation is integrable or not. So, if we use the integrability condition, that means x dot curl x, it becomes 0 for this given equation. And if we look at this equation, the function px, the coefficient of dx, the coefficient of dy and coefficient of dz can be separable if the equation is divided by x, y and z. So, dividing the given equation by x, y and z, it becomes dx by x, 2 dy by y minus 3 dz by z equals to 0. So, after integrating, we get an integral x y square equals to c z cube, where c is the integrating constant. This is method 3. In method 3, only one variable is separable. So, for this case, without any loss of generality, we assume that the coefficient of dx is only function of x, and q and r are function of y and z only. So, for this case, to become integrable this system, the integrability condition should be satisfied. So, if we use the integrability condition x dot curl x equals to 0, it implies del r del y must be equals to del q del x. That means q dy plus r dz becomes exact differential, and let that is d of psi. So, the given equation becomes px dx plus d psi equals to 0. So, after integrating, we can get the integral easily. So, this is the solution or primitive of the given equation. To illustrate that, we are taking one example: y square minus z square x square minus 1 dx minus 2 zx dy plus 2 xy dz equals to 0. So, first of all we have to check the integrability of this equation. So, for that we computed this x dot curl x, this is 0 for this example, therefore, the given equation is integrable and the given equation can be written in the form x minus 1 by x dx minus 2 dyz by y by z whole square minus 1. So, after integrating we can find the integral very easily, and this is the integral of the given equation where c is an arbitrary constant. Now, this is method 4. In this method 4 we are assuming that the function p, q, r are homogeneous function of x, y and z and they are of same degree n. So, for a homogeneous function, if we substitute this y is equal to e into x and z equals to v into x, the equation becomes this, and we can see that the variable x becomes separable and the other two expression a and b, this is a function of two variables and again it possesses an integral. Therefore, it is possible to find the integral for this case. We shall take one example to illustrate the idea of homogeneous equation. So, this is a homogeneous equation in x, y, z and they are of, it is of degree 3. So, here capital X is x square z minus y cube, 3xy square x cube. So, curl x equals to this and x dot curl x after simplification is 0. Hence, the given equation satisfies the integrability condition. Therefore, we can look for an integral of the given equation. Now, if we look at the expression for p, q and r, these are functions of x, y, z and of degree 3, not only function, they are homogeneous function of degree 3. So, the substitution we need to make y is equal to ux and z equals to vx. So, if you substitute this, that means now we are changing the equation from x, y, z to x u v. So, in terms of x u v, the equation with this substitution becomes this. And you can see that in this equation the term dx is separable and the function which is related to u and v, this is also integrable, and after integrating we get the integral y cube plus z x square equals to cx. And this is the fifth method, method of reduction. In this method we assume that one of the independent variable, say z, is constant. So, if z is constant, p dx plus q dy equals to 0 and let it has the integral phi xy equals to c, and here c is independent of x and y, but c may depend on z. Now, taking differential of phi and equating it with p dx plus q dy plus r dz, we will get an equation in c, x and y, and that will give the integral of the given equation. So, to clear that idea, we are taking one example. This is the example, x y square minus s square dx plus y x square minus z square dy minus z y square minus s square dz equals to 0. First we take y as a constant. So, if you take y as a constant, then the term, this term dy becomes 0. So, the equation becomes x y square minus s square dx minus z y square minus a square dz equals to 0, or in other words x dx minus z dz equals to 0, and this equation is integrable. We can find easily the integral of this equation as x square minus z square. So, in this case phi xz is x square minus z square equals to c, but you have to remember that this c is independent of x and z, but it may depend on y. So, phi xz is equal to c, c is function of y. So, if you take the differential of phi, then it will be like this, and if we compare this with the given equation, then we will get the relation in this form del c del y plus 2 cy y square minus a square equals to 0, and it is very easy to solve. So, after integrating we will get a relation like this: c into y square minus a square is equal to c dashed, and we also have x square minus z square equals to c. So, if we substitute the value of c here, x square minus z square, so this equals to c dashed by y square minus a square, or in other words the integral can be written in this form: x square minus z square into y square minus a square equals to c dashed. So, this is the required integral or solution of the given equation. And the last method is the method of auxiliary equation. In this equation, we try to find, or we try to write an equation, auxiliary equation, to find the solution of the Pfaffian differential equation. So, if this is our given equation and if we assume this is integrable, then it should satisfy the condition grad dot curl x equals to 0, and this condition leads to the equation p del q del z minus del r del y plus q del r del x minus del p del z plus r del p del y minus del q del x equals to 0. Now, x dot dr equals to 0 gives the equation p dx plus q dy plus r dz equals to 0. So, if we compare these two equations, then dx dy dz must be proportional to del q del z minus del r del y, del r del x minus del p del z, del p del y minus del q del x respectively, and this equation is called auxiliary equation. So, in this procedure, from a Pfaffian differential equation we are constructing an auxiliary equation which is a simultaneous equation. Now, using the methods of solving a simultaneous equation, we shall try to find the integral of the Pfaffian differential equation. Now, we shall use the method 6 to solve this example. Z into z plus y square dx plus z into z plus x square dy minus xy into x plus y dx equals to 0. So, first of all you have to verify the condition of integrability of this equation. So, x is this and grad of x is this. So, x dot curl x is equal to 0 for this equation. So, it implies that this equation is integrable. So, it is possible to find the integral surface of the given equation. Now, the auxiliary equation becomes this. Now, this is a simultaneous equation and we have already read how to find solution of a simultaneous equation in earlier module. So, in this equation we can solve taking these three equation in this way. This is the one integral x plus y into z equals to constant and xy minus z equals to constant. This is the another integral of this simultaneous equation. Therefore, these two equations together implies the equation solution of this equation, simultaneous equation. So, this is the solution of the given Pfaffian differential equation. In module 3 of chapter 1, we learned Pfaffian differential equation. We have established the necessary and sufficient condition for solvability of a Pfaffian differential equation, and we have also discussed 6 different methods for solving a Pfaffian differential equation in 3 variables. In this way, we end this module and chapter 1.